Hi, and welcome back to our rules of integration for vector-valued functions. We're going to pick up where we left off, which is trying to figure out how to integrate vector-valued functions in using some of the rules that you've known before. So let's get started. So on this one, we have r of t equals this whole thing, and really we're just, like I said, going to take antiderivatives and decide what we need to do with them, basically. So if I've got this first one, I have the integral of 2t dt, and that's going with vector I. And then over here I have the integral of t square root of 3t squared minus 5 dt, and that goes with j. And then over here I have the integral of 4t cubed minus 1/2 t dt, and that is 4k. And we're just going to take these one at a time. The first one should be super easy. I'm going to add 1 to the power, divide by the new power, and get a plus c. So there's that guy. The second one, now this next one uses u substitution, so that's the reason I have this in here as an example. Now you can either do u substitutions in your head if you're really good at them and you remember them, or you can actually write them out. So I'm going to write this one out and see how it works here. So remember, when you do a u substitution, I always tell my students that the u is most often the inside of the parentheses. And once you get your u sub, which is the inside, u equals 3t squared minus 5, your du isn't a choice, it's the derivative of u. So the derivative of 3t squared is 6t dt. And then what I usually tell my students is basically I want to take this second equation and make it replace what's left over in the integrand. So my integrand still has a t and a dt, but this has a 6t and a dt. So what I'd really be doing is multiplying both sides of this by 1/6. So then when I rewrite the integral, I have the integral of u to the 1/2 times 1/6 du, because t dt would be 1/6 of that second equation. Now that 1/6 can go out in front. Usually that's what we end up doing. And then when I go to take the antiderivative, I'm going to just add 1 to the power, divide by the new power, and put that 1/6 back with a plus c, which makes my second term in terms of t, let's see, 1/6 times 2/3 is 1/9, and then u to the 3/2 becomes 3t squared minus 5 to the 3/2 plus c. So there's the first component, there's the second component, and then my third component is just another backwards power rule. Add 1 to the power, divide by the new power, add 1 to the power, divide by the new power, and plus c. And again, these c's aren't all the same, so what I often do is c1, c2, c3, just to remind myself that they're not all the same value. All right, and then last but not least, just one more to kind of go through, get some derivative rules back under our belt. So I'm going to have the integral of 3t squared plus 1 over t cubed plus t minus 9 dt. This one I've got a quotient, I can't get rid of it, so I'm going to try a u sub. And when you do a u sub with a quotient, you usually want to make u the bottom. So if I let u be t cubed plus t minus 9, then du is going to be 3t squared plus 1 dt. Hey, that was handy because that's what I have on top. Fantastic. So this becomes the integral of du over u, whose antiderivative is ln absolute value of u plus c, which makes my first term of my vector r of t is ln absolute value of t cubed plus t minus 9 plus c1. And then my second guy here, I have the integral of 1 over t plus 12. Now you can do this with a u sub, but I'm just going to give you the shortcut. When you have a constant over a linear, your antiderivative is always an ln, and it's the ln of the bottom times 1 over the derivative of the bottom. And again, this only works for antiderivative of a constant or a scalar over a linear function. But this is going to be ln t plus 12 is a nice shortcut, plus c. So I'll stick that over here, ln absolute value t plus 12 plus c2. And then last but not least, I've got the integral of 1/3 cos 3t dt. The antiderivative of cos 3t is going to be, what, sine 3t? All right, but it's going to be sine 3t divided by 3, and I already had a 1/3, so this is going to be a 1/9 plus c, which makes my last guy 1/9 sine of 3t plus c3. Whew. All right, so just remember your integral rules. That was really the purpose of all of that. And this last page is just about what do you do with all those plus c's, because we have a lot of them. So if we're finding an antiderivative of, let's say, this guy, but I said, you know what, I'm going to tell you that r of 0, is 3, -2, 1. What we have to do with that is really just take the antiderivative and then solve for the plus c's. So in order to do this, really, we're just going to do everything we did before and solve for c. It's really not a big deal. And what I did was just select a couple other things of types of functions you need to know how to take the antiderivative of. So that being said, so if I have r prime is given, if I want to find r of t, I just need to evaluate each of these integrals. So the antiderivative of cos 2t dt is going to be 1/2 sine 2t plus c1. And then the antiderivative of -2 sine t is going to be +2 cosine t plus c2. And then 1/1 plus t squared has an antiderivative of inverse tan. That's just one you need to have memorized, plus c3. So there's my antiderivative for r of t. Now, from there, we need to substitute t equal to the value specified and solve for the initial conditions. So I need 1/2 sine 2 times 0 plus c to equal the first component of my initial condition, which was 3, -2, 1. So that guy should equal 3. And then if I look back up here, then I need 2 cosine of 0 plus c2 to equal, what's my second component? -2. And I need inverse tan of t plus c3 to equal the last component, which was 1. And I need that to happen at t equals 0. So sine of 0 is 0, so in this case, c1 equals 3. 2 cosine of 0 is 2, so 2 plus c2 equals -2, so c2 equals -4. And then inverse tan of 0 is 0, so c3 equals 1, meaning that r of t is specifically 1/2 sine 2t plus 3. And then what do I have next? 2 cosine t minus 4. And last but not least, inverse tan of t plus 1. And that's your antiderivative using the initial conditions. So la-ti-da, our integrals lesson is done. I hope you've enjoyed our time. My son is a huge Minecraft fan, so today we're going to have a Minecraft joke. The Minecraft joke is this: how does Steve from Minecraft get his exercise? By running around the block.